Ladies and gentlemen, we are going to spend just over 10 minutes taking a look, and I'm gonna go through here only very slightly, taking a look at three primitives that are widely supported within a functional context, that are supported in Python, that are supported in Scala, that are supported in Java 8, and in fact widely supported in a number of environments, which make processing of information and make, in fact, programming within the context of functional abstraction very convenient, but also very performant and very scalable when it comes to ability to handle large numbers of different processors. Okay, and these three primitives are map. We saw that last time. Reduce and filter. Okay, and I'm going to highlight each of these, and then we're going to explore them. Okay. Okay. So the idea here is that map, we saw it last time, represents a mapping of each element of a collection. Okay. So here we have a collection, and we produce a collection, and each element of the new collection is the result of applying a function that's specified to the corresponding element of the original collection. So we have a collection A. Maybe this is an array, maybe it's a vector, maybe it's a set with map values, maybe it's a hash table, one-type dictionary. We'll have each of these elements, and then we're going to create corresponding elements over here in this new collection, each of which is going to be the result of applying the function we specified to the corresponding element of this original collection. Okay, so this is applying f to this guy, we get this guy here. Applying f to this guy, we get this guy here. Okay, we did that last time. Do you remember that? Map of this thing, we applied map, and we, for example, could take an array of 1, 2, 3, and apply a square operator, and we get out 1, 4, 9. Right? Okay. Filter also takes a function and a collection. It operates on a collection with a function. So it's a higher order function. It takes a function in, or a closure in, more precisely. And it basically goes through and tests each of those elements. See which of them pass the test. Predicate that's passed in. The predicate is something that evaluates, does this element pass the test? And only those that are passed, a new collection is produced, but it consists of only those that pass the test. That make sense? So we might have a collection of, numbers from -1, from -100 to +100, and we filter out all those to include only those that are greater than or equal to 0, right? We get out those that are greater than or equal to 0, or we extract from a bunch of numbers only the primes, a bunch of natural numbers. Reduce is going to represent accumulation, and here represents accumulation in a general concept. So that accumulation might be, so here we got a collection in, we got a function, and that function tells us how to combine elements of the original collection. So we combine two elements into one. And by so doing, across that entire original collection, we're going to get out one value. Kind of summarizes the original collection, right? That's the sum of the original collection, or it's the product of the elements of the original collection, or it's the norm of the original elements of the collection, or what have you. So norm squared. Okay, so here we are summarizing or accumulating the original collection. So let's take a look at that. All right. there are a few minutes left, and let's make use of them. Okay, so here we go. I think I have a Scala window in here somewhere. Oh no! Oh, one more. Okay, let's check it out. Ah, the dream of centuries. Okay, so here we go. We're back to where we were last time. So here we're going to do val, array 1 equals array of 1, 2, 3, 4, 5, 6, right? Boom. Great. Here we go. Okay, this is taking some time. It's probably swapping it in from disk. Yep. I'm thrashing. A little bit too much loaded right now. I gotta evict this virtual box. I don't need that. That would spare us a lot of memory. Okay, come on. Okay, well, hopefully you folks will have time to draw up your Scala windows here. Okay, so let's do a map just to remember. How would I map, ladies and gentlemen? How would I map a square operator? And how would I square each of these numbers? Tell me what to write.
Underscore times underscore.
For squaring? Ooh, okay, if I do this, good idea. I like your thinking. What if I did that? What's the problem? These are in fact two different arguments. Okay, so it's actually going to be looking for two things here. This needs to be a function that takes one thing in. So what could I give it? What's that? I times I. Okay, that's great. Okay, great. So here we squared each of them. Okay. With nod to our math friends who might be perplexed to see that, because after all, that should be -1. But Anahita's from engineering, so we call it J over there. Okay, so ladies and gentlemen, we just mapped each of those elements. Each of those elements had this function applied to it. So over here, f is this function that takes in an I, and it returns I times I, right? Comfortable with that? Okay, so now let's do a filter. Filter. How would I tell it to filter out things that are greater than 3? Okay, I greater than 3. Yeah, that'll work. But aligned with what that gentleman said over there, I like the basic idea as a sound one. Here we go. Ready? So this is basically saying, hey, take the first argument and see whether it's greater than 3. It's implicitly a closure in there. It's take an argument which it doesn't bother naming. Whatever the first argument is named, just check if it, take that argument and check if it's greater than 3. Eh? We could check if it's greater than 1. Right? Great. So that will yield a new collection. Got or not? Okay. Cool. Okay, now let's do a reduce. Now the gentleman's idea enjoys merit. Let's try this. What is that? What number lies before me? What's the meaning of that? Whence did that come? Yeah, it's the sum of each of these. 1 plus 2 plus 3 plus 4 plus 5 plus 6. Gauss knew it immediately. You've heard the story. Gauss, when he was in, 2nd or 3rd grade. His teacher, I guess, was a bit frazzled for the whole class. And she asked this class of 1st graders or 2nd graders. She just wanted to keep them occupied so she could probably do some marking or something. So she said, okay, for this entire class, your job is to add up the numbers from 1 to 100 and give me the answer, okay? So she had all these kids, and they were adding up 1 to 100, and Gauss, Carl Friedrich Gauss, perhaps the most brilliant mathematician that's ever lived, he came up to her like within 2 minutes and said, "Here's my answer." and he had figured out, okay, wait a minute, there's a symmetry here. You know, you add 1 to, actually it was from 1 to 99, if you want to add 1 to 99, you get 100. You add 2 to 98, you get 100. And so he just figured out, okay, you just, multiply 100 times 49, add 50 or something like that. So he gave her the solution. And she was not happy. Like, oh man, now I've got to teach a lesson.
So is it the same Gauss as the Gaussian distribution?
Sorry?
Is
Yeah,
it
it's the same Gauss. Yes. Yes. A worthy name that's extended has influenced many areas. Okay, so ladies and gentlemen, here we've reduced this to 21, okay? Add 1 to 6, you get 7. 2 to 5, you get 7, right? And 3 and 4, you get 7. And so you get 3 7s times each other is 21, right? Okay, how if I did times? What would I get? 6 factorial, ladies and gentlemen, 720. This is telling us how to accumulate, how to summarize, right? Given 2 elements, it tells us how to combine them to get 1 element. And from that, it'll apply this successively to all the elements. Yes?
For the mapping function, why didn't we use the underscores?
For map, we could have. There would have been nothing wrong for some of these. Let's suppose that if I had said this, okay? So instead of writing this, I could have written instead this. Oh, sorry. There we are. Same, right? But what happens if I do this? So I would suppose I wanted to have this. Could I write this? No, because it's expecting 2 arguments. You can see it's looking. So each of these, it's not the same underscore, in short. This one is not the same, not referring to the same thing. These are 2 different ones. That's how Scala interprets that. Each time it appears, it's a different argument. But we could do it for reduce, because here, what we're giving it is something that takes, let's be very clear about this, it takes in, and I hope I get this right in terms of, because I want to get you out of here. This is what this really is. We're taking an I and a j, and we're returning something that's I times j here. And the reason we can give 2 is because we're expecting 2 arguments. This argument corresponds to the I, this to the j. And same thing with this guy. That's what this is. This is a summarization operator. It says, given 2 elements, how do I summarize the results? Here by adding them together. And having given that, we can then apply that to the whole darn array, ladies and gentlemen. To this array here. By applying it successively to that array. And it's applying that to get a summary for the whole array. And it turns out, ladies and gentlemen, that these operators can be applied in parallel to tens of millions, hundreds of millions of things at the same time. Sort of. There's actually some dependencies when it comes to reduce, for example. You've got to have, you can do it in a log, a time comparable to the log of the number of items. Map, do it parallel. Filter, parallel. Okay? We'll talk about it more next time. Thank you very much.